Hello and welcome to this video tutorial on the most promising battery technologies for electric vehicles. As EV adoption continues to grow, advancements in battery technology are critical to improving range, efficiency, and sustainability. In this session, we'll explore the key trends shaping the future of EV batteries. We'll start by understanding the increasing demand for EV batteries and the challenges with current technology. Then, we'll discuss why lithium-ion batteries remain the dominant choice today. But most importantly, we'll dive into the next generation of battery technologies: solid-state, lithium-sulfur, sodium-ion, silicon-anode, and graphene batteries, each offering unique advantages that could revolutionize the industry. We'll also look at industry leaders and cutting-edge research driving these innovations forward. By the end of this video, you'll have a clear understanding of the most viable battery technologies shaping the future of electric mobility. So, let's get started. According to IEA.org, demand for batteries and critical minerals continues to grow, led by electric car sales. Increasing EV sales continue driving up global battery demand, with fastest growth in 2023 in the United States and Europe. The growth in EV sales is pushing up demand for batteries, continuing the upward trend of recent years. Demand for EV batteries reached more than 750 gigawatt-hour in 2023, up 40% relative to 2022. Electric cars account for 95% of this growth. Globally, 95% of the growth in battery demand related to EVs was a result of higher EV sales, while about 5% came from larger average battery size due to the increasing share of SUVs within electric car sales. The United States and Europe experienced the fastest growth among major EV markets, reaching more than 40% year-on-year, closely followed by China at about 35%. Nevertheless, the United States remains the smallest market of the three, with around 100 gigawatt-hour in 2023, compared to 185 gigawatt-hour in Europe and 415 gigawatt-hour in China. In the rest of the world, battery demand growth jumped to more than 70% in 2023 compared to 2022, as a result of increasing EV sales. In China, plug-in hybrids accounted for about one-third of total electric car sales in 2023 and 18% of battery demand, up from one-quarter of total sales in 2022 and 17% of sales in 2021. Plug-in hybrids batteries are smaller than those used in battery electric vehicles, thereby contributing less to increasing battery demand. In recent years, Chinese carmakers have also been marketing more extended-range EVs, which use an electric motor as their unique powertrain but have a combustion engine that can be used to recharge the battery when needed. Extended-range EVs typically have a battery size about twice that of a plug-in hybrid, enabling a real-world electric range of around 150 kilometers compared to 65 kilometers for traditional plug-in hybrids. With an ICE on board, extended-range EVs can reach ranges of around 1,000 kilometers when needed. In 2023, extended-range EVs accounted for 25% of plug-in hybrid sales in China, up from about 15% in 2021 to 2022. The rapid growth in EV adoption is reshaping global battery demand, with regional markets evolving at different speeds. While plug-in hybrids contribute to sales growth, their smaller batteries limit their impact on overall demand compared to battery electric vehicles. Emerging technologies like extended-range EVs are gaining ground in China, signaling a shift toward more flexible electrified solutions. The data underscores the importance of battery size and regional preferences in driving the future of EV energy storage. In recent years, lithium-ion batteries have revolutionized the way we store and utilize energy, powering everything from smartphones and laptops to electric vehicles and renewable energy storage systems. As the demand for efficient and sustainable energy solutions continues to rise, so too does the need for advancements in lithium-ion battery technology. Energy density refers to the amount of energy stored per unit volume or weight of the battery. Over the years, researchers and engineers have made significant strides in increasing the energy density of lithium-ion batteries, allowing for longer-lasting battery life and extended driving ranges in electric vehicles. Innovations in electrode materials, electrolytes, and battery cell design have contributed to these improvements, paving the way for more efficient energy storage solutions. Another area of focus in lithium-ion battery technology is reducing production costs to make electric vehicles and renewable energy storage systems more affordable and accessible to consumers. Advances in manufacturing processes, economies of scale, and material sourcing have helped drive down the cost of lithium-ion batteries in recent years. Additionally, research into alternative materials and recycling initiatives aim to further lower production costs and reduce reliance on scarce resources. Ensuring the safety of lithium-ion batteries is paramount, particularly as their applications expand into critical sectors such as electric vehicles and grid storage. Advances in battery management systems, thermal management techniques, and cell design have led to significant improvements in battery safety. These enhancements help prevent issues such as thermal runaway and cell degradation, reducing the risk of battery fires and malfunctions. One of the primary challenges in lithium-ion battery technology is scaling up production to meet the growing demand for electric vehicles and renewable energy storage systems. Establishing large-scale manufacturing facilities requires substantial investment in infrastructure and equipment, as well as skilled labor and supply chain management. Lithium-ion batteries rely on scarce and finite resources such as lithium, cobalt, and nickel, which raises concerns about long-term availability and geopolitical risks. As demand for these materials continues to soar, securing a stable supply chain becomes increasingly challenging. While lithium-ion batteries offer significant environmental benefits compared to fossil fuel-based technologies, they are not without their environmental challenges. The extraction, processing, and disposal of battery materials can have adverse environmental impacts, including habitat destruction, water pollution, and carbon emissions. Developing environmentally sustainable practices for battery manufacturing, recycling, and disposal is essential to mitigate these concerns and minimize the environmental footprint of lithium-ion batteries. Among all battery chemistries, from the old-school lead-acid to nickel-based and even high-temperature Zebra batteries, lithium-ion stands out as the clear leader. Here's why. First, energy density. Lithium-ion packs more power into a smaller, lighter package than lead-acid, nickel, cadmium, or nickel-metal hydride batteries. This means longer-lasting smartphones, laptops, and electric vehicles that go farther on a single charge. Second, no memory effect. Unlike nickel-based batteries, lithium-ion doesn't lose capacity if you don't fully discharge it. Just plug it in anytime, no hassle. Third, efficiency and speed. Lithium-ion charges faster, wastes less energy, and holds its charge longer when in use. Compare that to lead-acid, which struggles with slow charging and high self-discharge. Fourth, longevity. While a lead-acid battery might last 300 cycles, lithium-ion delivers thousands, making it cheaper over time despite a higher upfront cost. And let's talk versatility. From tiny wireless earbuds to massive grid storage systems, lithium-ion scales effortlessly. Zebra batteries need extreme heat to work, and nickel-cadmium contains toxic cadmium. Lithium-ion avoids these pitfalls. Yes, lithium-ion isn't perfect. It needs careful management to prevent overheating, and mining its materials has environmental challenges. But with recycling improving and new tech like solid-state batteries on the horizon, lithium-ion's lead will only grow. So, whether it's your phone, your car, or the renewable energy grid, lithium-ion is the backbone of our electrified future. For EV use, the most popular batteries are NMC, lithium nickel manganese cobalt oxide, and NCA, lithium nickel cobalt aluminum oxides, which combine metals with nickel and cobalt to make them last longer and hold the most energy. However, LFP batteries, also known as lithium iron phosphate, is the new emerging lithium-ion chemistry used for EV batteries. Compared to NMC and NCA chemistries, LFP batteries have the following advantages. Cost savings. LFP batteries are cheaper to produce, and that means more affordable EVs for a wider demographic of shoppers. NCA battery cells cost about $120 per kilowatt-hour, NMC at about $113 per kilowatt-hour, and LFP as low as $98 per kilowatt-hour. Longer life. LFP batteries have a longer cycle life, meaning they can be used from full to empty, more times than NCA or NMC batteries. This is a part of why Tesla recommends charging your LFP battery to 100% once a week, but capping charged for nickel-based batteries at 80%. More resistant to aging from fast charging. Although our preliminary Tesla results indicated that occasional fast charging does not have any drastic, short-term effect on range, laboratory science has shown us that NCA and NMC batteries are sensitive to long-term degradation from frequent high-voltage, high-heat charging. The same is not necessarily true of LFP batteries. This is because LFP batteries rely on a 3D, crystalline structure, and can withstand high temperatures without decomposing. Lower fire risk. Lithium-ion battery fires are usually due to extreme heat conditions, and are triggered by something called thermal runaway, which happens when the temperature of the pack exceeds a certain limit. For LFP batteries, thermal runaway temperature is at 270 degrees Celsius, as compared to 210 degrees for NMC and 150 degrees for NCA. This makes them super safe for on-the-road uses. Fewer environmental and ethical issues. Because they avoid cobalt and nickel, LFP batteries can produce, on average, 15 to 25% lower carbon emissions than NMCs. They also avoid some of the humanitarian criticisms about battery manufacturing. Lithium iron phosphate, LFP, batteries are gaining traction due to their safety, longevity, and cost-effectiveness. The image on the right highlights key EV battery manufacturers and their cell compositions. LFP chemistry is prominently produced by SK Innovation, CATL, and Graphene. LFP batteries offer advantages such as improved thermal stability, longer cycle life, and lower costs, making them ideal for mass-market EVs. However, they have a lower energy density than NMC or NCA batteries, which can impact vehicle range. Despite this, LFP is increasingly favored for its reliability, especially in entry-level and commercial EVs. Solid-state batteries have emerged as a promising solution to address the limitations of traditional lithium-ion batteries. These batteries offer the potential to revolutionize industries ranging from electric vehicles to renewable energy systems. By replacing the liquid electrolyte found in lithium-ion batteries with solid materials, solid-state batteries aim to enhance safety, increase energy density, and extend the overall lifespan of energy storage systems. The main difference between solid-state batteries and lithium-ion batteries is the state of their electrolytes. Traditional lithium-ion batteries have a liquid or gel electrolyte, whereas solid-state batteries employ solid electrolytes. The figure on the left illustrates the structural distinctions between solid-state batteries and lithium-ion batteries. The positive and negative electrodes act as either anode or cathode depending on whether the device is charging or discharging. A range of solid electrolytes are currently being explored and include ceramics, polymers, resins, and glass composites. There are some safety concerns posed by lithium-ion batteries due to their flammable nature that may be improved by solid-state batteries by reducing the risk of leakage, thermal runaway, and dendrite formation. In addition to improving safety, all solid-state batteries also offer higher energy densities compared to traditional lithium-ion batteries. This means that solid-state batteries can store more energy in the same amount of space, making them especially attractive for applications that require compact energy storage solutions like electric vehicles and portable electronics. Having unique transport, thermal and mechanical characteristics, solid-state batteries can also potentially address the major issues encountered with lithium-ion batteries and overcome fast charging limitations. The development of solid-state batteries represents a significant step forward in energy storage technology. Their potential to enhance safety, increase energy density, and enable new applications holds promise for a more sustainable and efficient energy future. While challenges remain in terms of material development, manufacturing, and performance optimization, ongoing research efforts and advanced instrumentation are steadily pushing the boundaries of this technology. As these hurdles are overcome, solid-state batteries could reshape industries and play a pivotal role in the global transition to cleaner and more efficient energy systems. Lithium-sulfur batteries represent a promising next-generation energy storage technology that operates through a fundamentally different chemistry than conventional lithium-ion batteries. These batteries generate electricity through electrochemical reactions between a lithium metal anode and a sulfur-based cathode. During discharge, lithium atoms oxidize at the anode, releasing electrons that power devices, while the lithium ions migrate to the sulfur cathode where they react to form various lithium polysulfide intermediates before ultimately producing lithium sulfide. This chemical process offers significant advantages, particularly in energy density, as each sulfur atom can theoretically host 2 lithium ions, enabling much greater energy storage capacity per unit weight compared to traditional battery materials. Ongoing research continues to advance lithium-sulfur batteries toward viability through innovative solutions like nanostructured carbon-sulfur composites, advanced electrolyte formulations, and protective anode coatings. The technology's potential benefits, including higher energy density, lower material costs, and reduced environmental impact, make it particularly attractive for applications where weight is critical, such as electric aviation and long-range electric vehicles. While lithium-sulfur batteries may not replace lithium-ion in the immediate future, they represent an important development pathway that could eventually overcome current limitations through continued materials science breakthroughs and engineering innovations in battery architecture and manufacturing processes. Lyten has successfully manufactured lithium-sulfur batteries using existing lithium-ion production lines, achieving over 90% yield. Their process eliminates toxic solvents and reduces costs while maintaining compatibility with standard equipment. A sulfur cathode and lithium metal anode have the potential to hold multiple times the energy density of current lithium-ion batteries. Lyten uses that potential to build a practical battery without heavy minerals like nickel, cobalt, graphite, or iron and phosphorus. The result is an up to 50% weight reduction versus NMC and up to 75% weight reduction versus LFP. Lyten's lithium-sulfur battery has also higher energy density than NMC but built with lower-cost materials than LFP. The company plans to deliver commercial cells in 2024 for aerospace and government applications, with potential for EV use. Lyten's technology avoids nickel, cobalt, and graphite, offering an eco-friendly alternative to lithium-ion batteries. The rapid expansion of sodium-ion battery technology marks a significant shift in energy storage solutions, offering a viable alternative to lithium-ion batteries by utilizing abundant, low-cost materials. Global sodium-ion battery production capacity is projected to grow by 230% in 2024, adding 50 gigawatt-hour of new capacity, as industries seek to diversify away from lithium supply constraints. Structurally similar to lithium-ion batteries but using sodium ions instead of lithium, this technology presents distinct advantages and trade-offs. While sodium-ion batteries currently offer lower energy density, around 160 watt-hour per kilogram, due to sodium's larger ionic size and mass, they now approach the performance of entry-level LFP batteries, between 120 to 200 watt-hour per kilogram. Their unique properties, including superior performance in extreme temperatures, from -40 to +60 degrees Celsius, high power capability, up to 10 C discharge rates, and enhanced safety, make them particularly suitable for energy storage systems, light electric vehicles, and specialized applications like cold climate automotive systems and backup power for data centers. A key advantage lies in material sustainability. Sodium-ion batteries eliminate dependence on scarce lithium, cobalt, and nickel, instead using globally abundant materials, iron and manganese in cathodes, hard carbon, from biomass or petroleum byproducts, in anodes, and aluminum current collectors instead of copper. Sodium carbonate, the primary raw material, costs 100 times less than lithium carbonate. This not only improves supply chain resilience but also reduces geopolitical risks associated with critical mineral sourcing. Despite these benefits, sodium-ion batteries currently face economic challenges. While material costs are lower, manufacturing at scale remains more expensive than mature lithium-ion production. With lithium prices returning to pre-2021 levels and LFP battery costs at historic lows, sodium-ion adoption is progressing gradually, initially in cost-sensitive energy storage system applications and short-range mobility. Looking ahead, benchmark Mineral Intelligence forecasts sustained growth for both technologies. While global battery demand will reach 3.5 terawatt-hour by 2030, with energy storage system demand tripling by 2030, potential lithium-ion supply shortages could emerge by 2034, creating opportunities for sodium-ion batteries to complement rather than replace lithium-ion solutions. The technology is particularly promising for applications where cost, safety, and temperature resilience outweigh the need for maximum energy density, positioning sodium-ion as a crucial component in diversifying the world's energy storage portfolio. Silicon-anode batteries represent a major leap forward in energy storage technology, offering the potential for significantly higher energy density and faster charging compared to traditional lithium-ion batteries with graphite anodes. Silicon's ability to store up to 10 times more lithium ions than graphite could enable batteries with longer life and greater capacity, making them ideal for electric vehicles and portable electronics. Additionally, silicon anodes facilitate quicker lithium-ion movement, allowing for faster charging and improved power output during discharge cycles. These advantages position silicon as a key material for next-generation batteries. However, the widespread adoption of silicon anodes faces a critical challenge: extreme volume expansion. When lithium ions are inserted during charging, silicon can swell by 300 to 400%, causing mechanical stress that cracks the anode material and degrades battery performance. This expansion also leads to electrolyte consumption and the formation of an unstable solid electrolyte interface (SEI) layer, further reducing battery lifespan. Additionally, the high cost of advanced silicon materials and the difficulty of scaling up production present significant hurdles for commercialization. To overcome these challenges, researchers are developing innovative solutions. One approach involves nanostructuring silicon into nanowires or nanoparticles, which can better accommodate volume changes without fracturing. Another strategy combines silicon with carbon materials like graphene or carbon nanotubes, improving conductivity while mitigating expansion effects. Solid-state batteries present another promising avenue for silicon anodes. By replacing liquid electrolytes with solid alternatives, these batteries could eliminate issues related to SEI instability and electrolyte degradation. Companies like Stordot and Amprius have already demonstrated silicon anode batteries with impressive fast charging capabilities and energy density. Despite these breakthroughs, scaling silicon anode technology remains a challenge. Manufacturing processes must be refined to reduce costs and ensure consistency in large-scale production. Automakers and electronics manufacturers are closely monitoring progress, as even partial adoption of silicon anodes could significantly improve battery performance. Hybrid designs, which blend silicon with graphite, are already entering the market as a transitional solution. Looking ahead, silicon anode batteries could revolutionize energy storage if key obstacles are addressed. Their superior energy density and charging speed make them ideal for applications where performance is critical, such as EVs and grid storage. While pure silicon anodes may still be years away from mass adoption, incremental improvements and hybrid approaches are paving the way for their eventual integration. Graphene, a sheet of carbon atoms bound together in a honeycomb lattice pattern, is hugely recognized as a wonder material due to the myriad of astonishing attributes it holds. It is a potent conductor of electrical and thermal energy, extremely lightweight, chemically inert, and flexible with a large surface area. It is also considered eco-friendly and sustainable, with unlimited possibilities for numerous applications. In the field of batteries, conventional battery electrode materials, and prospective ones, are significantly improved when enhanced with graphene. A graphene battery can be light, durable and suitable for high-capacity energy storage, as well as shortened charging times. It will extend the battery's life, which is negatively linked to the amount of carbon that is coated on the material or added to electrodes to achieve conductivity, and graphene adds conductivity without requiring the amounts of carbon that are used in conventional batteries. Graphene can improve such battery attributes as energy density and form in various ways. Lithium-ion batteries, and other types of rechargeable batteries, can be enhanced by introducing graphene to the battery's anode and capitalizing on the material's conductivity and large surface area traits to achieve morphological optimization and performance. It has also been discovered that creating hybrid materials can also be useful for achieving battery enhancement. A hybrid of vanadium oxide and graphene, for example, can be used on lithium-ion cathodes and grant quick charge and discharge as well as large charge cycle durability. In this case, vanadium oxide offers high energy capacity but poor electrical conductivity, which can be solved by using graphene as a sort of a structural backbone on which to attach vanadium oxide, creating a hybrid material that has both heightened capacity and excellent conductivity. In addition to revolutionizing the battery market, combined use of graphene batteries and graphene supercapacitors could yield amazing results, like the noted concept of improving the electric car's driving range and efficiency. While graphene batteries have not yet reached widespread commercialization, battery breakthroughs are being reported around the world. Despite efforts from the US and EU to secure local domestic supply, all major EV battery manufacturers remain based in Asia. In the left infographic we rank the top 10 EV battery manufacturers by total battery deployment, measured in megawatt-hours, in 2023. CATL has swiftly risen in less than a decade to claim the title of the largest global battery group. The Chinese company now has a 34% share of the market and supplies batteries to a range of made-in-China vehicles, including the Tesla Model Y, SAIC's MG4, and various Li Auto models. In 2023, BYD surpassed LG Energy Solution to claim second place. This was driven by demand from its own models and growth in third-party deals, including providing batteries for the made-in-Germany Tesla Model Y, Toyota BZ3, Changan UNI-V, Venucia V Online, as well as several Haval and FAW models. The top three battery makers, CATL, BYD, LG, collectively account for 2/3, 66%, of total battery deployment. Once a leader in the EV battery business, Panasonic now holds the fourth position with an 8% market share, down from 9% last year. With its main client, Tesla, now sourcing batteries from multiple suppliers, the Japanese battery maker seems to be losing its competitive edge in the industry. Overall, the global EV battery market size is projected to grow from $49 billion in 2022 to $98 billion by 2029, according to Fortune Business Insights. The chart on the right compares various battery chemistries based on specific energy and energy density, key metrics that influence electric vehicle range and packaging. LFP batteries offer solid safety and long cycle life but has lower energy density and specific energy than other chemistries, limiting range. LFP batteries are ideal for cost-effective, entry-level EVs. NMC advanced lithium-ion variants offer progressively higher energy content, suitable for long-range EVs and performance applications. Lithium-sulfur cells are promising next-generation option with very high specific energy, potentially suitable for aviation. Sodium-ion batteries represent emerging technology with moderate density, more sustainable and cost-effective. Lithium titanate batteries have very low energy figures but excellent fast charging and cycle life. They are more common in stationary or low-range applications. In conclusion, the landscape of battery technologies for EVs is rapidly evolving, driven by the need for higher energy density, improved safety, longer life cycles, and cost-effectiveness. Emerging technologies such as solid-state, lithium-sulfur, and silicon-anode batteries offer promising improvements in energy density and specific energy, potentially enabling longer ranges and faster charging. Thanks for watching. Share the video and subscribe for more technology and engineering content.